Welcome to the glass plate. In one of the previous examples we computed heating up of water in a cooker. We had about half a liter at a given temperature of water and we put in heat. In this exercise I'm going to call that P, the production of heat inside the control volume. We ignored that when the water and the cooker heat up, that there will be a flow towards the surrounding, a flow of heat. In this exercise we're going to take that into consideration. And we're going to model that in the following way. The loss from the cooker is proportional to the temperature difference of the water temperature in the cooker minus the surrounding. Makes sense. The hotter the water, the more you expect, the more heat you expect to flow out. If the temperature of the water is the same as the surrounding, you expect nothing to happen. We're going to put a coefficient beta in front of this, which has a numerical value of 5.3 watts per Kelvin. So if this is 20 degrees temperature difference, multiply that by 5.3 and you have the heat flow in joules per second flowing out. Our water is initially at 20 degrees. The surroundings is at 20 degrees and that will stay so. And we would like to heat up the water from 20 to 80 degrees Celsius. And the question is, how long does that take if there is a loss? Well, we know what to do. We need to set up an energy balance. We already considered that in a previous example. And we have that the internal energy, so the change of temperature, equals 0 minus the outflow plus the production, this P. You could also say that's an inflow, then this becomes a 0 and the P moves over to an inflow, gives the same equation. We know that we can write this from a previous example as mCp dt over d time, and we have this one coupled to the temperature difference. Okay, so we have set up our balance. I can even write, if I want, for this density of water times V. We're going to assume that densities, specific heat, those quantities are constant. In reality, if you heat up water, they are not, but to simplify stuff, we do that, and they don't change very much. So the answer is not critically depending on this. Thus, I can write down the differential equation for the temperature, which reads as d temperature d time equals, this one contains the temperature, so that's going to be minus beta over mCp times T minus T of the surroundings plus P. This is the equation that we have to solve, and that is a little bit more complicated, or rephrased, quite a bit more complicated equation than we had before. You can try and work out the solution yourself, or you can try and look that up via internet, and you will get that the temperature with respect to the surrounding temperature equals some constant times an exponential function, which has as coefficient minus beta rho VCP times time plus, I need to divide this, plus P over beta. Yeah, this is the solution of this differential equation with an unknown integration constant popping up here. I had to integrate once. Okay, now you need to fill in that at time equals 0 we have the initial condition known, temperature T0, and then you can work out this alpha. And that alpha in itself is, if you do that, T0 minus T inf minus P over beta. With this I have the total solution fixed and I can compute the required time when is the temperature 80 degrees. For that you need now to wait 152 seconds, which is substantially longer than in the previous case when we even let the temperature go to 100 degrees, but there were no loss terms. So you see that the loss term slow down the entire process, which is logical. You put in heat, but it flows out, so it's less effective. This shows you that the same type of energy equation can now be used to incorporate that you have loss terms. Your differential equation is relatively easy to back out. Solving it is much more difficult, but there are mathematical ways to do it, and this solution is known. Once you have this, yeah, sure, the answer is not too difficult to find.